In this video, we're going to look at two ways we can handle events in Unity Dots. Events are very powerful, but as you know, Dots is all about being data-oriented, so that means we have to be smart in order to implement events which are object-oriented. Let's begin! Hello and welcome, I'm your Code Monkey, and this channel is all about helping you learn how to make your own games with in-depth tutorials made by a professional indie game developer. So if you find the video helpful, consider subscribing. Okay, so here we're going to cover several ways of handling events in Unity Dots. First of all, if you're not familiar with Dots, then check out the playlist linked in the description. I've also covered C# events in another video, so check that out. Events are excellent for helping keep your code clean and making sure that your scripts are nicely decoupled from each other. However, events are normally object-based, which makes them tricky when applied to Dots, which is data-oriented and very heavy on multi-threading. Now, Unity Dots is still early in development, which means the best practices aren't yet known, so that's why here I will cover two different possible ways of handling events. First, I will cover handling events using a native queue and a struct for our event type, and then for the second method, we're going to do it by creating entities and adding an event component. Then in the end, I will showcase a nice complete class I built in order to make events very easy to use, which as always you can download included in the project files. Okay, so here is the demo scene. I have my player object over here working as an entity, and when I press space, I can make it jump and pipes start being spawned. This is taken from a project I've been working on, trying to make Flappy Bird completely with dots. So if you're watching this in the future, then check the link in the description. The Flappy Bird Dots project should be out within about a week. So now our test here is we want an event to be fired whenever we go through a pipe. The way that this is set up is the player never actually moves horizontally, the pipes are the only ones that are moving. Here is the game and the scene view side by side, and you can see the player is always right down the middle, right on x equals 0, and the pipes are the only ones moving. This video is made possible thanks to these awesome supporters. Go to patreon.com/unitycodemonkey to get some perks and help keep the videos free for everyone. So over here is the pipe move system. It is pretty simple. All we're doing is an entities for each, cycling through every single pipe and grabbing the translation. Then we are modifying the translation based on a move direction, moving it to the left by a certain move speed and delta time. But before we do that, we store the X position before moving, and then we store the X position after moving. And our event test is right here. First, we're testing if the X position before is above 0 and afterwards is below or equal to 0. Then it's in here that we have passed the player and we want to fire off our event. So here it is again, I start jumping and pipes start coming and I go through the pipe and it's in there that I want the event. Alright, so let's start off by making our very basic event. So here inside of this system, let's just define a public event of type event handler, and let's just call it onPipePassed. So when the pipe passes the player. So here it is, a very basic event. If you want to learn more about events in C#, then check the video linked in the description. Now let's start with one approach based on using a native queue. So during our entities for each, we're going to have our native queue, and over here we're going to add our event onto the queue. And then after the job is processed, then we're going to read through the queue and fire off our event. So first, we need our native queue. So we define it as a private native queue. And now here we need a type. So let's define a basic event struct to be our type. So just a public struct. Let's call it our pipe-passed event. And now here we could also add a field if we wanted our event to have extra information, but in this case let's keep it simple, and all we want to do is know when this event happens. So you create a native queue of this type. So we have our event queue, and now in order to initialize it, let's go into protected and override the onCreate method. And in here we construct our event queue. Now here we pick our allocator, and in this case let's use persistent. So we're going to use the exact same queue every time we run the system. And since we're using persistent, then we also need to make sure to deallocate it. So let's also override the void on destroy. And in here we just do event queue.dispose. Okay. All right, so here we have our very simple native queue that contains elements of pipe-passed event. Now down here we need to pass the event queue onto our job. And here, in order to make sure that our job is actually running correctly in parallel, then instead of using the event queue directly, we need to use a native queue parallel writer. So here we define a native queue of the same type, and we're going to use the type parallel writer. And we simply get it by going into the event queue and as parallel writer. Okay. And now we can use this one safely inside of our job. So when we have the event, let's simply enqueue something onto our queue, and let's just pass in our pipe passed event. And that's pretty much it. Very simple. We just have our queue and we enqueue an event whenever something happens. Now, after we schedule our job, here is the somewhat tricky part. See, what we're doing all the way up here is we're only scheduling the job. So by the time we get to the code down here, then this job has not yet actually run. It has only been scheduled. So if the job hasn't run, then that means the native queue hasn't actually been filled. And the job system is also smart enough to know that this one is being used, so we can only read from the queue after this job completes and finishes writing to it. So just to see the error, let's try reading the queue anyways. So we do a while, go into the event queue, and we try to dequeue. So just like this, we have our event. And let's test. And there it is, right away we can see our error. It's essentially saying that we cannot read from this native queue before the previous job has completed. So the way we make this work is by completing the job. So before we try to dequeue, let's go into our job handle and call complete. So this will make sure that the job completes, which will free up our event queue, so we can then safely read it. And now if we run, here we are and start jumping and yep, no error, and we go through the pipe, and yep, there you go, we have our event. Now let's test using the actual C# event. So here let's create a new script, call it just testing.events. Let's create a new game object and attach our script onto it. Okay, now here in our basic monobehavior script, let's test our event. So let's go and make a private void start. And on start, let's subscribe to our event. So here first, let's access the entities world. So we need using unity.entities. And then here we can access the world, access the default game object injection world to get or create the system of type of our pipe move system. So we have reference to our system, and then inside we have our very nice event, and we simply subscribe like normal. So here we just do a debug log on the pipe event. Now finally, we just need to actually trigger our event. So back in our move system, in here, instead of doing the debug log, we simply do our event and simply invoke it. All right, so there it is. Let's test. Okay, here we are. Let's start jumping. And as soon as we go through the pipe, yep, there you go. We have our pipe event. Awesome. So just like this, we have a job component system working in the entities world, and it is firing a regular C# event, which we can then capture from anywhere. So for example, we could capture this event on the UI to do something. So here we have our first way of handling events. And the pattern is pretty simple. Essentially, we just need to create an event queue that lives inside of our system. So we make it persistent. Then inside our onUpdate, we construct a parallel writer so we can work multi-threaded. Then we do our normal entities for each. Whenever we have something that we want to fire an event, we use the parallel writer in order to enqueue our event. Then afterwards, we force the job to complete, and we simply try to dequeue every event inside of our event queue. And once we do, we simply call our regular C# event that we can listen from anywhere. And again, here we are jumping, and we go through a pipe, and there you go, we have our piped event, so everything is working perfectly fine. Great! Now, if you're familiar with how the job system works, then you will have noticed how calling complete here will have some consequences. Essentially, we're creating a sync point. We're stopping the rest of our game whilst this job is completing. That is obviously not ideal. Ideally, we want to make this job, but then let the job system decide when it should be completed. So one approach we can take to try to solve that problem is to create another system. So here I have another system, and now we can make sure that this system runs at the end of the frame by using the attribute update in group. Then we can pass in the group for the late simulation system group. And just like this, now this system would run at the end of the frame. So then in here, we could call complete on our job. And in doing so, we would make sure that we would only actually try to complete right at the end of the frame. However, as you can see, that means that we need to store a reference to the job so we can access it from this system. So we need to store this and expose it. Then we also need to expose the queue. And we would need to handle the event in a different way since we can't evoke it directly from another system. So this approach of having a separate system would be better for performance, however at the cost of increased complexity. So here is the first way of handling events. We're using a native queue inside of our system. Now let's check out the second method, which will be based on creating an entity and adding an event component. So here we have the system back on its starting state like we saw before. Now this approach is going to be based on creating an entity and adding a component onto it. So first let's make that event component. So in here we can simply make our public struct, let's call this the event component, and we simply implement iComponentData. Okay, here's our very simple component. And now when we have our event, we want to create an entity and add our component. So the simplest way would be we go into the entity manager and call create entity. However, when using the entity manager, we are forcing a sync point, so this would break everything related to our job threads. So instead of using the entity manager directly, we need to use a entity command buffer in order to queue up our actions. So let's create one. In order to do that, we need to access the command buffer system. So let's grab it on our protected override on create. We go into the URL in order to get or create the system of type and simulation command buffer system. This is the command buffer system that runs right at the end of the simulation. So let's store this. Okay, we have a reference to our command buffer system. And now in here we access the system in order to create a command buffer. So this returns an entity command buffer. And in here this works the same way as the native queue, meaning we do not use the entity command buffer, but rather we use the entity command buffer .concurrent. So this is the same as the native queue .parallel writer. And we grab it by going into the command buffer and to concurrent. Alright, so we have a concurrent struct of our entity command buffer. And now this is what we can use down here on our job. So we simply use the command buffer in order to create an entity. Here for job index, we pass in the entity in query index. And just like this, we are creating an empty entity. However, we don't want it to be empty. We want it to have our nice event component. So if we inspect this function, you can see that there's a version that takes an archetype, so we can use that. Let's go up here in order to construct our entity archetype. And in order to construct, we simply access the entity manager and call create archetype. And we pass in our type of our event component. So now here we have an entity archetype and we can use it when creating our entity. Alright, so just like this, it should be working. Whenever the pipe passes the player, we're going to create an entity, and that entity will be added with the event component. Now we just need one thing, which is to make sure that the entity command buffer actually runs after this job completes. So we need to make sure that we add this job as a dependency to our and simulation command buffer system. So we just go in here and we add job handle for producer and we pass in this job handle. So this ensures that our command buffer will run only after this job handle has been completed. Okay, so let's test. Okay, here we are. So let's go through the pipe and now pause. And now we can look into the entity debugger. And here we see all of our entities, and right down here we see a new entity. And yep, there it is, our newly created entity with our event component. Awesome. Okay, so we have our entity being created with the event component being added when the event is triggered. Now we need to go through our entities and look for this event component. So back in our script, after we do everything, let's do an entities.forEach. And we're going to look for entities with our event component. And when you do find them, then in here, let's fire off the event. So let's define the event like we did previously. So event handler. There it is, we have the onPipePassed event, and in here we simply invoke it. Now in order to access this, we need to be running on the main thread, so we do an entities.forEach and we call run. Now after we run, we want to clean up and destroy all of the entities with our event component. So to do that, we can simply use the entity manager and call destroy entity. And in here there's a version which takes an entity query, so we can get our entity query of type of our event component. So this will destroy all the entities with our event component. Okay, so this seems like it would work, however we have several issues. Now, first of all, by default, the entities for each will be using burst. However, we cannot access references while using burst, so if we try to run like this, yep, there it is, we got an error right away. So we need to make sure that we call run and use without burst. So we do entities without burst and then the normal for each, okay? And now we still have the same issue that we had with the native queue method, which is that down here, all we have is our job has been scheduled. It has not actually run. So if we run the code just like this, there you go, over here we have an error. The error is because we're using the entity manager to modify the list of entities, but we cannot do that once the job still requires a reference to those entities. So down here we're trying to access the entity native array, but we cannot modify it since it's currently been scheduled to run on this job. So one way we can solve this is by ensuring that the previous job completes, very much like we did previously. So here we simply call job handle.complete. So here we are, and it looks good, and as soon as we go through the pipe, yep, there you go, we have our pipe event correctly being fired. Awesome! So just like this, we have our second method working. We create an entity command buffer. Then when we have our event, we write to the command buffer the action to create an entity and add our event component. Then afterwards, we complete our job, and we cycle through all of our entities that have the event component, and if we find some, then we invoke our event. And after doing so, we destroy all the entities with our event component. Okay, so here you can see our second method working. Now, the one issue here is we are creating a sync point. So as soon as we get in here, we stop in order to complete the job. So that means the whole game is going to be paused whilst this job is working. Now, the benefit of this approach is that we can listen to events on the exact frame that they happen. So as soon as an event happens up here, we catch it down here. And the downside is that we're forcing the game to stop whilst our job runs. However, right now we're actually both pausing the entire game and listening to events on the next frame. So the reason is actually all the way up here. We're using a command buffer created on the end simulation system. So that means that the command buffer will only run at the end of the simulation. Now, in order to actually listen to events on the same frame, we need to manually make a new command buffer and handle it ourselves. So here, instead of getting the command buffer from the system, we can do a new entity command buffer. Let's allocate with the temp job. Everything else goes through the same, okay. Then here we do not add the job handle for producer, but instead we go into the command buffer and we call playback, pass in our entity manager, and then we make sure to dispose of our command buffer. Now, to test that the events are happening on the same frame, let's go up here and add a field onto our event component. So let's add a public double, call it elapsed time. And in here, let's go and pick up the time.elapsed time. And this is also how we add more information onto our events. So in here, we create that, then we get our created entity. And then we can use the command buffer in order to set the component onto our event entity. And we set the new component and we pass in the elapsed time. And then down here, when we listen to our event, let's print both. So let's do a debug log on our event component.elapsed time. So the elapsed time inside the event component, and then also the one that we captured up here. So now we can test if we're capturing the event on the exact same frame, if both of these are exactly the same. So let's test. Okay, here we are, and let's go. And as soon as we pass the event, and yep, there you go, you can see the numbers. So you can see 7.565,565. Yep, there you go. So here we have the event firing correctly, and we can indeed verify that they are happening on the exact same frame. Awesome. Now, again, as I was saying, the issue with this approach is we're pausing the game in here whilst the job completes. So if we don't absolutely need to have our events be triggered in the exact frame, then we can essentially let the code run and only test for the events that happened on the previous frame. So here, let's not call job handle.complete, and let's go back to using the end simulation command buffer. So let's get this and remove this. Okay, so everything's the same as previously. So doing it like this means that we're not going to have this code actually run before we run this code. So essentially, when we go through the entities in here, we're going to go before the command buffer runs, so we won't be running one frame behind. And if we run like this, we're going to have the same error that we saw before, so we cannot use the entity manager in here. But what we can do is create another command buffer. So we construct a new command buffer, and as we go through our entities with events, then in here we can queue up the action to destroy the entity, and we pass in this entity. And yep, just like that. Alright, so now this should be working. Let's test. So here we are and jump, and as we go through the pipe, and yep, there it is, we have our event being fired. And if we look at the timing, you can see that the event was fired on 4.80, and yet it was captured on 4.81. So the event was actually triggered in one frame, and then we only captured it in the next frame. The benefit of this approach is we'll let the job system handle whenever it's going to run the pipe move system. So if you don't absolutely need the event to be caught in the exact frame that it's fired, then this approach would be better since it would let the game continue uninterrupted. So here is the complete second method. We define a iComponent data for our event component, and then we use a entity command buffer in order to construct an entity and add our event component. Then afterwards we read through all the entities with that component, we fire off the event, and we destroy that entity. So this is the second method fully working. Now over here I have two nice classes that I wrote to handle events based on the entity method. They work with generics, so they should be usable in just about any scenario. So this one uses the approach where it runs on the exact same frame, and this one uses approach on the next frame. I think the entity method is likely better than the native queue method, so that's why I made both classes using this approach. And I also made them to be as easy to use as possible. So if you want, you can inspect it yourself to see how it works. It seems like a lot of code, but it's really doing the same thing that we tried to do in here. So let's see how we can use this in the simplest way possible. So here is the pipe move system using that very nice class. So as you can see, you define the normal C# event. Then on create, we construct our nice object. As you can see, it's working with generics. So as a generic, we would pass in a certain component type for our event. So in this case, we'll be working with this nice pipe passed event. You can define your own component with whatever values you want. Just one thing, the way that I set up, it is necessary for the component to have at least one field, even if you don't use it. The reason is because later we're doing an iJob for each, which does not work on empty tag components. So we construct our object using our event component. Then down here we have the normal entities for each. So before we do that, we go into our .events object in order to get an event trigger. So this is a struct that we can use safely inside of our entities for each. Then in here, when we have our event, we simply call our trigger event. And then we have two methods. We can either pass in the event if we want to set it to a certain value, or we can use a simplified version which simply creates the event with the archetype containing our event component. In this case, we're also passing in a value. Then afterwards we schedule, we get our job handle, so the same as previously. And then we use our .events object to call capture events. We pass in the job handle where the events were scheduled, and then we pass in a simple delegate to handle our events. So the delegate receives our event component. And then we do whatever action we want to do with our events. So here we're invoking our normal C# event, and we're also printing the values just to test if this is working on the same frame or the next one. So in this one, I'm using the last version on the next frame, so let's test. Okay, so here we are, and we start jumping, and we go through the pipes, and yep, there you go, we have our event. And you can verify that this one is using the version where it captures the event on the next frame. So it's fired on 343, and it's captured on 344. And now here, if I had an instance where I wanted to use the other method that captures on the same frame, all I really need to do is use the other version. So .events, use the same frame, change all of these, and yep, there you go, everything else is exactly the same. And now if we test, here we are, and we go through, and yep, there you go. Now you can see that we are now capturing on the exact same frame. So here you can see how this class is extremely simple to use. We just need to define it, define the component for our event. Then we get the struct that we can use in our job, we fire off the event, and we capture the events. Very simple. Both of these classes are included in a project file, so feel free to use them in your own projects. Alright, so here we saw two approaches for handling events. One using a native queue, and one using an entity and an event component. Again, dots is still in development, so the best practices aren't yet known. Perhaps one of these has some benefits or some cons over the other that I'm not aware of. Or perhaps a completely different approach will win out. If you know another way of doing C# events in dots, then please post it in the comments. Either way, here you have two possible ways of handling events. Events are extremely important, so with this, it should really help out when trying to make a game as much through dots as possible. If you're watching this in the future, then check out the video where I made Flappy Bird almost entirely in dots. For example, the connection between the dots world and the normal UI is handled using these events. This video is made possible thanks to these awesome supporters. Go to patreon.com/UnityCodeMonkey to get some perks and help keep the videos free for everyone. As always, you can download the project files and utilities from UnityCodeMonkey.com. Subscribe to the channel for more Unity tutorials, post any questions you have in the comments, and I'll see you next time.